Welcome to Genius Panda Virtual Labs, where students and teachers access the virtual laboratory simulations for various science subjects. Hello, dear learners. In this lesson, we will study the acid-base solutions and how we can use a simulation to describe acid and base solutions. According to Rwanda Education Board, this topic is covered in Unit 16, Acids and Bases of Senior 4 Chemistry, A-level chemistry. However, because this topic is covered in Senior 4 and Senior 6, as well as a very introductory part which is covered in Senior 2 and even in Senior 1, here we will limit our discussion to the introduction. So it will be the first part of the simulation acid-base solutions. And the second part, which is covered in Senior 6, will be discussed in another video. Here we have the objectives of our lesson. At the end, we should be able to define acids and bases, and then use a lab simulation to describe the difference between a strong acid and a weak acid, as well as a strong base and a weak base. Here we have some key points. What is an acid? What is a base? There is a common definition, and in Senior 4, we consider that to be the Arrhenius theory. Arrhenius theory of acids and bases says that an acid is a substance which can produce H-positive ions in aqueous solution. We have an example of HCl. And a base is a substance which can produce OH ions in an aqueous solution, such as a substance sodium hydroxide. So this is an acid according to the Arrhenius theory, and this is a base according to Arrhenius theory. And we have another theory, the Bronsted-Lowry theory. Here, an acid is defined as a proton donor. It is not necessary that the substance should be able to dissociate in an aqueous solution. So any substance which can give a proton, whether in the gaseous phase or in aqueous phase, that substance is an acid according to Bronsted-Lowry. And a base is a proton acceptor. The example here is ammonia. Ammonia in the gaseous phase can react with hydrogen bromide, for example, and in the gaseous phase, there is no production of OH ions. So you can say that the Arrhenius theory we have here, it excludes this ammonia, for example, which is behaving as a base, even though it doesn't produce this OH, it doesn't give the OH in gaseous phase. When, for example, hydrogen bromide reacts with ammonia to produce ammonium bromide, you can see there is no OH involved. So the ammonia simply is a proton acceptor, and hydrogen bromide here is a proton donor. So that is Bronsted-Lowry theory. And there is another Lewis theory, and there is another theory, which is Lewis theory, defining an acid as a lone pair acceptor. Here we have the example of cations like a copper 2 positive, substances which are electron deficient as boron trifluoride. These can accept lone pairs, so they are acids according to Lewis, and a base is a lone pair donor. Any substance which has a lone pair it can share is a base according to Lewis. We can also give the example of ammonia. Now, what is a strong acid? What is a strong base? What is a weak acid? What is a weak base? A strong acid or a strong base is the one which dissociates completely in aqueous solution. And this is also defined as a strong electrolyte. So this concept can also be used, and even the simulation somehow can be used by senior 2 students, where they study the strong electrolytes and weak electrolytes, because strong acids and bases, they are also strong electrolytes. Weak acids and weak bases, they are also weak electrolytes. So when it is said to be strong, it means that it dissociates completely. Here we have examples of hydrogen chloride, sulfuric acid, sodium hydroxide, potassium hydroxide. These two are acids and these two are bases. So we have substances which can dissociate completely, and those ones are strong acids, strong bases. Strong bases, strong acids. A weak acid or base dissociates partially in aqueous solution. So, for example, when you take, let's say, 1,000 molecules of CH3COOH and dissociate them, you will find that a small fraction of the molecules will dissociate. Let's say like 50 will dissociate, and 950 will remain undissociated. So only a small fraction of the molecules will dissociate. But for the strong acids and bases, there is a complete dissociation. You use 1,000 molecules, and all of the 1,000 molecules will dissociate. But for weak acids and bases, only a small fraction, like this 50, for example, will dissociate. So, and this we have here are examples. The first two, they are acids, and these two are bases. According to Bronsted-Lowry theory, there is also what we call an acid-base conjugate pair. And when we have two species which differ by a single proton, those two species, they make what we call an acid-base conjugate pair. For example, the HCl and the chloride ion, this is a conjugate pair. You can see when HCl reacts with NH4, sorry, when it reacts here, I mean NH3, what we get is NH4 plus Cl negative. It's the equation we have here. Now, this one is a proton acceptor. After accepting a proton, it becomes a proton donor. Now it can give, in this form, it can give a proton. So it is a conjugate acid. And this one, which has given its proton, now it can accept a proton. So it is a conjugate base. And you can see the difference between HCl and Cl negative is a single proton. The difference between ammonia and the ammonium ion is a single proton. So these species, they form what we call acid-base conjugate pairs. And what it means here is that this is a strong acid. When it produces a conjugate base, how will the base be? This base will be a weak base because it is produced from a strong acid. And this acid, the conjugate acid, which is produced from a weak base, will be a strong acid. So every time, if you have a weak acid or base, the conjugate species that will be produced will be strong. And if you have a strong acid or base, the conjugate species that will be produced will be weak. To mean what? To mean that, for example, here, this is a weak acid, so the conjugate base it produces is a strong base. Good. Now let's go to the simulation and see how we can use the simulation to explain what is an acid, what is a base, what is a strong acid, what is a strong base, and the weak acid as well as weak base. What are the characteristics of these substances? How can we use the simulation to distinguish them? So let's start with water. Here we have water, here we have a strong acid, here we have a strong base. We have a strong acid here, here we have a weak acid, strong base, and weak base. And here we have the molecules, molecular representations of the species which are involved in the equilibrium. We have various tools here. This is a tool used to check for the pH, okay? And here it is a universal indicator, and here it is an electric circuit we can use to check for the conductivity of our solution. And here we can show the molecules. You can see here we are showing the molecules. This HA stands for the acid, and this H2O is the solvent. When the acid is put in water as a solvent, there is a dissociation. How will the acid dissociate if it is a strong acid? We will look at that. First of all, let's start with water. With water, we can consider this to be an autoionization of water, where the two molecules of water will combine, giving this acid and this base. But you can see we have equal species, and with the equal species, what do we get? What will be the pH? We click here on the tools and we check for the pH. The pH of water, pure water, is 7, because the concentration of the base and the concentration of the acid in the solution, they are the same. If you want to check, you can use even the graph here. And with the graph, you can see that we have 1 times 10 power negative 7 and 1 times 10 power negative 7. So we have same concentrations, and the pH will be neutral. We go back to the molecules, and now we see what happens when we have a strong acid. Do you remember how we defined a strong acid? If you don't remember, now you pause the video and think about it. A strong acid has been defined as the one which dissociates completely. So let's look at what happens when we use a strong acid in the simulation. You see, we have, this represents a molecule of the acid, and this is for water. Let's remove the solvent molecules. There we have removed the solvent molecules. You can also add them. You see the difference. And when we remove them, it's like that. Now you can see we don't have these molecules in our solution. What does it mean? This means that the acid has completely dissociated. You can see there is no more HA in the combined form. There is no molecular acid. But we have these new species which have been dissociated. Now, what is the pH of this solution? Because it is a strong acid, it has a very low pH, a pH of 2. Okay? And now let's use the indicator, the universal indicator. This one will change color depending on the pH. Here we have put there in the solution, and we move it on this side. To move these buttons, we always use your mouse, and you make a left click and hold it down, and then you slide. So I slide like this. You can see where the colors are resembling. So the pH is almost 1 or 2. The pH is 2. We have a pH of 2, showing that this solution is strongly acidic. The solution is strongly acidic. What happens when we use this other tool? We will, because we have all the molecules which have dissociated to give a lot of free-moving ions, then we would expect this solution to be a very good conductor of electricity or very poor conductor. You think about it. Of course, it will be very good. We have so many ions. You can see the light here, very shiny, because we have a strong electrolyte. We said that strong acids, strong bases, they are also strong electrolytes. Now, let's go to a weak acid and see what is the difference. When we use a weak acid, remember, this represents the acid molecules, and here we have water molecules as the solvent. What do we have? You can see these molecules of the acid, a very big number is still there in the solution, undissociated, representing the partial dissociation we have said. You can see only a small fraction has been dissociated. Only a small fraction. We have so many molecules which are in the undissociated form, and only a small fraction has been dissociated. So this is a weak acid. What happens to the pH? The pH, you can see it's slightly acidic. We have a pH of 4.5. And with this universal indicator, when we use the indicator here, you see the color is almost between 5 and 4, or 5 somewhere here. So this is a weak acid. And when you use an electric circuit, as one could expect, what do you expect? To get the light like the one of a strong acid. See, the light is different. Let's change here a bit to let you compare well. You see, the light here is very shiny, but for a weak acid, it's less shiny. So this is because we have a small number of molecules that have dissociated, okay? So here also, as I said, we can use the graph. When you use this graph, let's remove this electric circuit. When you use a graph, you can see that we have a very high concentration of the dissociated spaces. And here we have a negligible concentration of the combining acidic molecules. So there is a very high concentration of the dissociated spaces. And with the weak acid, you can see that the concentration of the combined spaces is very high compared to the concentration of dissociated spaces. Okay? Of course, because here we have a monoprotic acid, an acid which can produce a single proton, then we have the same number of negative parts and positive parts. Now let's go to the strong base. With a strong base, here we have our basic molecule, and this one represents the combined form. And here we have the dissociated spaces. Because this is so strong, it will, of course, be the same as this strong acid. The combined form is negligible, but the dissociated form is very high. You can see the concentrations. It will be the same for the pH. We have a very high pH. A pH of 12 means that the solution is very basic. If you use a universal indicator, you put it in the solution, you see the color here. It's 12, similar to 12. And if you use the electric circuit, you put it in the solution, there is a lot of light. The light is very high. Why? Because we have a lot of free-moving ions in this solution. And what happens with the weak base? Before we look at the weak base, now let's remove the graphs and we go to the molecules. You see, the molecules, we don't have any combined form. In the dark gray here, we don't have any combined form. Everything we have, it's only the yellow and the blue, the dissociated form. So this is a strong base because it dissociates completely. With a weak base, this is what happens. You can see we have the base here, and this is water molecules, and here we have the dissociated spaces. The base, you can see it is still there in the combined form. This represents the combined form. So the combined form is present in a higher concentration than the dissociated form. And this shows that the solution is a weak base solution. You can check on the pH. The pH is 9.50. This is a pH for weak bases, weak basic solutions. And you can also use the indicator. If you put it in the solution, you see it is in the 10 and 9, okay? 10 and 9. And when you use the electric circuit, you see the light is not that shiny. So much shine. The light is not so much shiny. The light is not so much shiny because we have a small number of dissociated species as well as the free-moving ions. So this is all for the first part, the introductory part. We have distinguished the strong acids and weak acids, strong bases and weak bases, and we have seen the different ways we can use to distinguish these strong and weak acids and bases, and we know how we can use the simulation to demonstrate that, the differences. Now it's time for those who are ready. If you think that you are ready, it's time to go to the quiz. Here we have the quiz code. If you are ready to take the quiz, it is VID 001009. If you have not well understood and mastered the content of the video, you can replay and replay to get a better mastery of the content, and then you will come back for the quiz later. But if you are ready, and maybe you are new to the system, here are the steps to follow when you are taking the quiz. Remember the code for this quiz, the specific quiz for this video, it is VID 001009. And you go to opanda.xyz, you click on login, it's here in the blue color. And after that, you click on take a quiz. Take a quiz, it's here. Take a quiz, and after clicking on take a quiz, this window will appear, and you type in here the code VID 001009, and then you take the quiz. I hope you enjoyed the lesson. See you next time.